Welcome to Selection with Sathi. Today we will master heaps and priority queues with code on screen. A heap is one of the most versatile data structures in computer science. We will cover the Max-Heap Property, Heapify, build heap, extract max, insert, heap sort, and priority queue operations. This topic is heavily tested in GATE CSE and coding interviews. Let us begin. Let us start with the Max-Heap property. A heap is a complete binary tree stored compactly in an array. Look at lines 3 to 5. The parent of index I is I minus 1 divided by 2. The left child is to I plus 1, right child is to I plus 2. In a max heap, every parent is greater than or equal to its children. This means the root, at index 0, always holds the maximum element. The height of a heap with n elements is floor of log base 2 of n. For a min heap, we simply reverse the comparison, parent is less than or equal to children. Now let us look at Heapify, also called Sift-Down. This operation fixes a heap violation at a single node. Look at line 2. We assume the current node I is the largest. Lines 5 and 6. If the left child exists and is larger, update largest to left. Lines 7 and 8. Similarly check the right child. Line 10. If largest changed, we swap the current node with the largest child. Line 11. Then we recurse on the child position to push the smaller value further down. This takes O of log n time because we traverse at most the height of the tree. Building a heap from an unsorted array is surprisingly efficient. Look at line 4. We compute the last internal node as n divided by 2 minus 1. Leaf nodes, which are indices from n over 2 to n minus 1, are already valid heaps. Line 5, we loop from the last internal node down to the root, calling Heapify at each. You might think this is O of n log n, but the tight analysis shows it is actually O of n. The reason, most nodes are near the bottom and need very few swaps. Only the root might need log n swaps, but there is only one root. This O of n build time is a classic gate proof question. Extract max removes and returns the maximum element from the heap. Look at line 4, we save the root value, which is the max. Line 5, replace the root with the last element in the array. Line 6, remove the last element by popping. Line 7, call Heapify at the root to fix the heap property. The last element, now at the root, sinks down to its correct position. This ensures the next largest element bubbles up to the root. Time complexity is O of log n for the single Heapify call. Inserting a new key into the heap uses sift-up or bubble up. Look at line 2, we append the new key at the end of the array. Line 3, the new element starts at the last index. Lines 5 through 9, we compare with the parent. If the new key is larger, we swap up. Line 9, move I to the parent position and repeat. This continues until the parent is larger or we reach the root. The new element rises to its correct position in the heap. Time is O of log n in the worst case, when the element bubbles all the way to the root.
Let us build a max heap from the array 4, 10, 3, 5, 1. The array has 5 elements, so the last internal node is at index 1. Heapify at index 1, node 10 with children 5 and 1. 10 is already larger than both, no swap needed. Heapify at index 0, node 4 with children 10 and 3. 4 is less than 10, so swap 4 and 10. Array becomes 10, 4, 3, 5, 1. Now recurs on index 1, node 4 with children 5 and 1. 4 is less than 5, swap them. Final array 10, 5, 3, 4, 1. The max heap is built. Root 10 is the maximum. Now let us extract the maximum from heap 10, 5, 3, 4, 1. Line 2. Save max value 10. Line 3. Replace root with the last element 1. Array becomes 1, 5, 3, 4. Line 5. Call Heapify at root. Node 1 has children 5 and 3. 1 is less than 5, so swap. Array becomes 5, 1, 3, 4. Recurs on index 1, node 1 has child 4. 1 is less than 4, swap. Final array 5, 4, 3, 1. We extracted 10 and the remaining heap is valid. Let us insert 15 into heap 10, 5, 3, 4, 1. Line 2. Append 15 at the end. Array becomes 10, 5, 3, 4, 1, 15. New element is at index 5. Its parent is at index 2, which holds 3. 15 is greater than 3, so swap. Array becomes 10, 5, 15, 4, 1, 3. Now I is 2. Parent is at index 0, which holds 10. 15 is greater than 10, so swap again. Array becomes 15, 5, 10, 4, 1, 3. Now I is 0, we have reached the root. Stop. 15 bubbled all the way up to become the new root. Heap sort combines build heap and extract max. First, build the max heap, 4, 10, 3, 5, 1 becomes 10, 5, 3, 4, 1. Now swap root 10 with last element 1. Array 1, 5, 3, 4 then 10. Heapify the first 4 elements 5, 4, 3, 1. Swap root 5 with the fourth element 1. Array 1, 4, 3 then 5, 10. Heapify 4, 1, 3. Swap root 4 with third element 3. Array at 3, 1 then 4, 5, 10. Continue until done. Final sorted array 1, 3, 4, 5, 10. Heap sort is O of n log n and sorts in place with O of 1 extra space. Priority queues use heaps for efficient scheduling. Insert task A with priority 5. Heap has 1 element. Insert task B with priority 8. B has higher priority, bubbles to top. Now extract max, B with priority 8 is removed. A remains. Insert task C with priority 3. Heap has A at 5 and C at 3. Python's heapq module is a min heap, so we negate priorities for max behavior. Push -5 for A, -8 for B. The smallest negative is the highest priority. Priority queues power Dijkstra's algorithm, Huffman coding, and job scheduling.
Quick exam tips. First, a heap is always a complete binary tree. All levels full except last, filled left to right. Second, build heap is O of n, not O of n log n. Gate loves asking this. Know the summation proof. Third, memorize the index formulas. Parent is I minus 1 over 2, left is to I plus 1, right is to I plus 2. Fourth, heap sort is O of n log n worst case and in place, but it is not stable. Gate compares it with merge sort, which is stable, and quick sort, which has O n squared worst case. For more DSA concept videos with code on screen, download the Selection with Sathi app. Like and subscribe. Thank you.